All right, so hello everyone. My name is Alexandru Iosup. I'm here to talk about LDBC Graphalytics, which is one of the, I think, three benchmark types as part of the LDBC offer. This is work that definitely could not have been done without a variety of sponsors, so I'd like to thank them. Some of them are even here, so double thanks. And the large team that is actually distributed between Amsterdam and Delft. So for people who don't necessarily know where and what Vrije Universiteit and Technische Universiteit Delft are, you can see a little map and the relationship with Germany. Now, whenever I start whatever I'm doing, I'm asking myself whether I have time for it, and I guess this is shared by you. So let me give you a few pointers as to why I think you should actually invest your time in graph processing. So first, if you have any academic inclination, I'm glad that this morning one of my PhD students finally finished the analysis of, let's say, major conferences in computer science, in computer systems. So I'm a computer systems person. And we looked at titles and we tried to figure out what are the important keywords. And you know where I'm heading. First, if you look at the presence of keywords, and we looked at the top 50 in the past 5 years and their evolution. So you see here columns in blue represent no change, so the same keyword progressing over the years. And you see +1 means that the keyword gained a place, and -1 means that +1 on green means that the keyword has gained a place, and -1 means that it has lost. This is not necessarily so important. Clouds are everywhere in computer systems. That's not what I'm here for. But what I am here for is to tell you that actually if you look at the presence of the term graph in these top conferences and journals, then I think we have pretty good news. So the presence has actually increased. We started around the 36th position 5 years ago. Yeah, so it's the 36th most used keyword in top computer systems conferences. Now we are at about 29. And I think we're getting on the right direction of the linear regression. Warning, linear regressions can lie bigly. So maybe, maybe we shouldn't trust them. All right. But there's also a very clear motive. Graphs are definitely everywhere. I see them even on the T-shirts of the Neo4j team. Thanks for stealing my thunder. So I like to point out that if you think about really practical examples, for me, LinkedIn is one of the great examples because it actually matches a real societal need. So trying to get people into work, it doesn't get more serious than that for me, with the actual needs of the industry. So the other side that actually builds countries. And if you think LinkedIn is interesting because it does all sorts of interesting things, you may actually know that there are hundreds of LinkedIns actually highly specialized in military domains, in medical sciences, in all sorts of, in academia, for instance, we have our own LinkedIns, I don't know, ResearchGate and whatnot. Mendeley of Elsevier. So there are all of these, and they are all doing pretty much the same thing. They're doing some form of graph analysis on trying to figure out what the users are doing, and they keep getting more users, so apparently the services they provide are useful, but also why their users are doing those specific things, and more importantly, why they stop doing those important things. So you can see also that they need to run all sorts of analysis algorithms on their data sets. What's perhaps more relevant for LDBC Graphalytics is that all these organizations do a lot of full graph analysis. And the reason is that they keep asking new questions, so they need to reanalyze the entire data set sometimes. But also they want to get the morning update, right, for business decision making. Yeah, so this requires the nightly analysis over the full graph. So full graph analysis is the topic of today. Now, if you think about it, in databases, you hear very frequently that there's a database storage engine and a database execution engine, and these two work together seamlessly, and everything gets processed super fast. In large-scale graph analysis, you still have a notion of a storage engine, but it becomes a bit more complex. You still have a notion of database processing, but now at large scale, this becomes more complex. But now you also have between the two, because of the scale, a phase of partitioning and distributing the data. And ideally what you would want, just like in databases, is that as you add more resources, and even if you complicate your queries, you could still do the analysis either in the same amount of time as you did it before, that's weak scaling, or faster, and that's strong scaling. All right, so these are notions that we want to explore in LDBC Graphalytics. So full-scale graph analysis, we focus so far on the processing part, so not on the ingestion and loading and partitioning of data, but that's what's going to happen also in the future. And what I am to tell you today is a bit the history of the benchmark. So how did we get to it? Why do we need it? What we have already in it, where we are heading, the directions for future work. So Tim and Wing in this room will actually tell you a bit about it. And then Wing will give you a demo of one of our 4 future directions, so that will take the next 20 minutes. By the way, if I still have 5 minutes, I would appreciate a 5. It's already there. Brilliant. So at large scale, things can get quite diverse, either because you have a team that thinks smartly in terms of algorithmics, or because you have an excellent team in systems, or simply because your engineering is superior. And what we have seen so far are tens of different large scale graph processing systems competing in the same space of processing entire graphs using specialized algorithms. So of course you would want to understand which platforms perform well. And keep in mind that I'm using the plural here. In our experiments, we haven't found yet the single platform that can do, everything well. So probably there are multiple platforms, but even for those that perform well, you may want to understand what to tune and what needs to be redesigned to get actually the superior performance that they are capable of, and perhaps do this systematically. So our idea is that with a benchmark, you could address exactly these kinds of questions. And it may not be necessarily surprising, because there are also quite a few of other benchmarks that have tried this. One of the things that you may observe when you go in the direction of processing data is that, first of all, data diversity matters. It really matters what kind of information you load into your algorithm, who may take one or another of the paths in trying to find your answer. There may be significant changes in performance depending on what kind of data you're loading then. Data set diversity matters. Similarly, what you do with the data matters quite a lot. So what algorithm that we're looking at matters quite a lot, and we've seen significant performance differences when we used on the same platform for the same data set, different algorithms. And for many of you, this does not come as a surprise. Last, I want to point out the diversity of metrics. Which metrics should you actually be interested in? If I hear runtime, well, it's very interesting. Which runtime? What is the system under test? What does it mean to have a warmed up system? What does it mean to include different components in a large-scale distributed system that includes numerous components that may not be subject to your control? So with this in mind, the major alternatives in the space of graph analysis, so full-scale graph analysis, are of course Graph 500. This is, in a sense, the de facto standard in high-performance computing. Yeah, a single algorithm, BFS. You also heard about it a bit earlier, and just a single type of data set, synthetic, not really representative, and one type of metric. Yeah. We have a bunch of other alternatives, but we think none of them is actually capable of providing what we provide. The notion of systematically benchmarking or exploring the diversity of algorithms, the diversity of data sets with the diversity of metrics that get reported. And that is pretty much Graphalytics. So if you take home only one message, what is LDBC Graphalytics? It's this notion that benchmarking should be done with diverse algorithms, diverse data sets, and a diverse set of reported metrics. Yeah? There's no magic, but apparently we seem to have been the first one to propose it. So Graphalytics in a nutshell. It's an LDBC benchmark, and it has the properties of a good, well-defined benchmark that Larry talked about a bit earlier. It contains a harness, so some tool that you can use out of the box to run experiments. It contains many classes of algorithms, diverse data sets, and a good set of experiments that lead to reporting diverse metrics that are really important in a large-scale environment, processing large-scale full analysis of graphs. It also contains a notion of a renewal process. So whenever you hear benchmark, if I would be in your shoes, I would think, what happens when the previous definition of the benchmark does not match what the systems do today? Either because we change the data sets, or we change the algorithms in our community, or the metrics are no longer relevant for your customers. So in that sense, we want to have also a renewal process. And it starts as a project looking in the direction of, okay, so we get these high-level metrics, but can we actually help the development teams of the tens of different graph processing platforms understand why things are not performing as they want them to, where to tune? If you think about it, it's just a good semi-possible, possibly fully automated exploration of choke points or bottlenecks in these systems. It's exactly what we do with our engineering teams every day. Can we get this more automated? And we think that because it has these nice properties, it would finally enable comparing community-driven and commercial platforms, and we have a few numbers to prove it. And we'll talk a bit later about first internal and later external competition, global competition that we want of platforms that do graph processing. All right. So I talked a bit about the harness. I will try to be very quick about this because I would like the team to actually explain the new features, which should take longer than what I'm saying. I'm not sure if that's possible anymore. So if you think about the harness, you can find plenty of information online. The docs are online. I think it's easy to find this. But in principle, the Graphalytics team has built a harness that you can get from GitHub. You can just deploy and therefore compare various kinds of platforms for which we have written drivers. But if you are a developer, pointed here in the middle of the slide, you may actually develop your own system and provide your own drivers for your own system. And the driver is something that allows your system to run the benchmark. And if you think about it, I talked about diverse algorithms. It makes sense that the drivers are actually you optimizing for your own platform the set of algorithms that are the core of the benchmark. Otherwise, we can write a reference implementation, but I keep hearing this, and I like very much how it sounds, our kiddie script approach to implementing your algorithms on your platforms and systems would result in inferior performance. Yeah? All right. And the rest, here we have, 12 different steps of what a benchmark harness should actually do, especially in a distributed environment, collecting information, doing all sorts of magic. That's already taken care of. I've mentioned the representative algorithms. So far, we support 6 classes of algorithms. And the way we actually focus on supporting or not one algorithm or one class of algorithms is simply by seeing proof of use. Now, the best thing we could do is to go to the entire community using graphs and ask them, what are you using as algorithms? And either through a survey or through actually tracing of their operations and reanalysis and recharacterization of the workloads, we could get this information. It's unlikely as you may think. So what we did is to take the next best proxy, which is to look in the top conferences publishing work in this field, computer systems and databases, and see what algorithms get mentioned and get used in the experiments there. And if you look at those, then you can get a bit of an understanding which algorithms are important for the community that represents the community that we actually aim for. That is the set of algorithms that we have selected. Yeah? The important thing is that through a renewal process, we might change these algorithms if in 2 years' time we figure out that the community is trying something else. Yeah? So,
that has a weakness, though.
Comparability of results, or
but it's also you're going to get stuck in a local optimum here.
Yeah.
The community's using it because you're using it because they're using it.
Yeah.
And I think we should also come up with some algorithms that are challenging.
I like very much the idea. Yeah? So let's discuss this. The idea that Hassan was just talking about is best exemplified by Graph 500. For some reason, it looks like every graph processing system needs to do BFS. It's the best algorithm and the only one. And everyone does BFS, and everyone optimizes for BFS. OK, where we get with BFS when we want to do something else, nobody knows. All right. In terms of data sets, we provide real-world data sets, and we use two synthetic generators, one of which, UPC, Arnau's name will be on many things. So this is a pretty good and proven generator of realistic data sets with Facebook-like properties. We provide a diverse set of experiments, of which the baseline set is the most important. It actually runs all data sets or data set types with all algorithm types on the same platform. Yeah? So you get a really good comparison. And we think that we're using quite modern software engineering practices. And I've seen actually a couple of Jenkinses running on laptop. Well, not Jenkins's interface is running on laptops here, so at least we're discussing about the same thing. The ongoing activity. So first of all, I've mentioned that we're very interested in comparing systems globally, hopefully fairly. And in that sense, there's going to be a demo from which I'm going to steal a couple of minutes. So there's going to be a demo about the current status of this. Then I talked about semi-automated tools to identify bottlenecks in your systems based on data collected through these benchmarks. Yeah, so we're trying to help you optimize your systems, but not generally, but rather for running the types of workloads characterized by the data sets and algorithms that we actually propose in the benchmark. We also have Granula, which is a tool for modeling, collecting, so monitoring information, analyzing it, and being able to present it online, possibly to distributed collaborative teams, where the data is extracted from graph processing systems. And last, the release of a full-fledged LDBC Graphalytics. So to anticipate the question, I think the question a bit earlier was maybe from Alistair, something like, when will we actually eat the dinner? Well, we have a nice roadmap, and the idea is that the global competition, so not the internal rounds we are doing right now, will start in June. So with this, I'd like to pass a bit the baton, maybe, yeah. Okay, Wing, can you join? If you want to join, if not, I'll continue talking. All right. Yeah. How much time is there?
In total for the two presentations, or for your presentation, is already gone. Time.
I see. Okay. Good luck, Wing.
Okay.
Yeah.
It's necessary.
Yeah.
All right. So for the interest of for the interest of the time, I will try to keep that in 1 minute. So basically, what you can expect is that we are doing a benchmark to actually tell you the measure of what is the processing speed of a certain graph processing system. But the more important question is to actually ask why they have a certain speed. And that is what we are trying to achieve with Granular, to first build a operation model for the system to see how they operate. And what you can see here is, for example, the super steps of Giraffe that's using 5 workers. And you can see that what you, for example, can observe here is like, you can see those gray gaps in between the super step where actually some of the nodes are doing nothing. And this is one of the example of why that's actually a imbalance in the workload, which is a kind of bottleneck that you can expect. And what we try to achieve with Granular is that we'll be able to observe this kind of bottleneck in an easier way. There's actually much to tell, but I don't really think the time allowed. So I will pass the mic back to Alex.
You can just go to the next slide, and I guess it's not.
Okay. Right, so maybe after the last slide you weren't quite up to speed with what Granular does, and it was a very complicated chart and something that only an expert could really understand. So why not take the human out of the loop and actually start automatically analyzing this kind of really detailed performance data. And instead of this time-consuming process, we go from whatever it was that's there on the left, this performance data, and we translate that into kind of broad statements about where you're likely going to find performance bottlenecks. So for example, if the tool I'm currently working on would then produce results like there's a 20% slowdown in this particular phase due to imbalance in computation. Or perhaps we notice that for 60% of the time we're bottlenecked by CPU, for 30% on network, and maybe 10% none of the resources seem to be bottlenecks. Right? This is really compact data that's really easy to understand, and that's actually actionable. Right? If as an engineer I'm going to decide I want to tackle our network issues, then you know you're going to gain at most 30% out of that. And if you do this at the different levels in a model at job-wide, but maybe also really detailed for specific components, right? Then depending on your expertise in these components, you'll be able to pinpoint exactly where in the system can I start making my improvements. And that's the goal of the project also of Granula, to aid users in understanding this performance data through automated analysis of bottlenecks. There are a couple of future directions, and I would really like to talk to people who are currently working on graph processing systems about how they do their performance engineering right now. But you can imagine that if you collect this data over time, you can do regression tests and not only see that performance has improved, but where has it improved, and by optimizing which resources, right? Maybe we're not only interested in one job, but we want to make more broad statements about our system. We really do well in this kind of thing. Then we can use Graphalytics to run a representative benchmark and gain insight out of that. And a third possible line of research for me would be to really look at low-level data, so hardware counters, that sort of stuff. All right. And then I think we move to part 2.
All right, so let me spend 1 minute wrapping it up, and then we'll pass it. Thanks, Tim. This works. Sounds good. All right, so to wrap things up, okay. I've mentioned that we have this standard benchmark. It collects information for you. We also have a full benchmark that contains a diversity of experiments that look at various different aspects in your system. All the results you obtain in this way are results that we would want you to share with the world through this global competition. And last, what you may want to do, and emphasizing what Tim has said, if you want to use the results internally to improve your system, run the full featured benchmark that collects tons of monitoring information, therefore slowing down perhaps things that you're doing. So that's not what you report to the world as this is my top performance, but it helps you understand where there are problems. We are now internally conducting various rounds of competitive evaluations of systems with Oracle, with Intel, with IBM and Huawei, and also with various commercial products. But mid-June, we want to launch a global competition, so that you can participate. If you have a graph processing system, please contact us, tell us that you want to do it so that we can help you join the process easily. To conclude, the main thing you want to remember about LDBC Graphalytics is the idea of comparing graph processing systems comprehensively using diverse algorithms, diverse data sets, and simply diverse metrics. Thank you for your attention. Wing will now demo our live archive. So what you can expect in terms of a competition. How would it look like? What would you get out of it? And how can you join? And I think it's more the exploration of a website. All right. Wing,
Sure.
Want to join? All right. Thank you.